So it's the starting of the lecture of Yon. Don't hesitate to interrupt him when you want. Thanks, Yon, to come here.
Good. Thanks. Thanks, Raphael, for the introduction, and thanks for the invitation to come here and to give this series of lectures. So after looking at the program, I realized that I'm off topic. So my talk will be kind of like, it will be maybe more mathematical than what you have seen in the past 2 weeks. But of course, I will try to be as pedagogical as possible. And this means that I need your help. So whenever things are not clear or they don't make sense, or you have anything you want to add, please stop me. We have a nice blackboard, so I can go into more detail or give some more clarifications about some different topics. So I will post these lecture notes on my website. So I'm a researcher in mathematical physics in Toulouse, and so my research topics are somehow around random matrix theory and quantum information theory. But today I decided to tell you about tensor norms. So basically my goal is to give you this kind of toolbox of tensor norms that appear all over the place in mathematics, but also importantly in quantum information theory. I decided to tell you about tensor norms in relation to quantum entanglement. So basically all that, most of maybe 80% of the 90% of the 3 lectures will be some reviewing basic stuff about tensor norms and entanglement. Give you a bit of references about these topics. So there are these 2 very nice books on quantum information theory with like a more mathematical focus. So you have the Nielsen and Chuang book on quantum information theory, which is kind of the Bible of the field. But these 2, Alice and Bob Mitbanach, and the theory of quantum information by John Watrous, these are more like mathematically flavored. So if you like to be more, if you like more precise definitions, theorems, and stuff, these are 2 very nice books. And there is also a blog post by Jordan Taylor, which explains a bit about tensors and graphical notation for tensors and some machine learning applications of this graphical notation, which I like a lot. Good. So again, please feel free to stop me whenever you want and come after and talk to me if you have any questions. Let me tell you a bit about my plan for these 2 lectures. So since I don't know a lot about your backgrounds, today I decided to go a bit slowly. So the plan for today is just to tell you about norms in general, so not tensor norms, and some basic stuff about norms like geometry of the unit balls and some duality, and then start talking about quantum information theory. And tomorrow we'll talk about tensors and start to see the first example of tensor norms and some applications to the entanglement of pure quantum states in the multipartite setting. This is where things get interesting. You go from 2 parties to 3 or more parties. And then in the last lecture on Wednesday, I want to discuss like the general theory of tensor norms. So go a bit more in depth in the abstract theory, and then talk about the entanglement of mixed quantum states, which is a completely different beast. It's more complicated than pure states because it makes sense, they are more general. And tell you how tensor norms can help us understanding quote-unquote entanglement and deriving some entanglement criteria in the bipartite and multipartite settings. So that's the plan, but of course, I mean, if we go slower, that's also fine. We don't have to cover everything. The important point is that things should be as clear as possible. Okay, good. So let me start with an appetizer, like what will these lectures be about? So is the text big enough, or should I make it bigger especially for the people in the back row? Bigger? It's okay? Good, so the main idea of these tensor norms is the following problem. I mean, you have two vector spaces with a norm, each one comes with a norm, and you want to define a norm on the tensor product of these 2 vector spaces, which kind of, if you take quote-unquote marginals, you get the two norms. You get the two initial norms. So how can we build out of two norms for individual vector spaces a norm for the tensor product of these vector spaces? And it turns out that there are many choices. There is no canonical choice. And among these choices that satisfy some conditions which are natural with respect to what I said, so they have to satisfy some compatibility conditions with the initial norms. There is a smallest possible norm and the largest possible norm. These are called the injective and the projective norms. So these are the two beasts that I want to discuss in these lectures. And, and there are many, many other choices in between this injective and the projective. So, for instance, in the case of matrices, if you have two matrices, the space of matrices you have of size D, let's say you have D squared parameters, and this you can see as a tensor product of RD, tensor product with RD. And it turns out that two of the most famous norms for matrices, the operator norm and the nuclear norm, so the largest singular value and the sum of the singular values, these are precisely these projective and injective tensor norms. When you put on the initial spaces on R2, you put the Euclidean norm. So kind of already this tells you that this kind of the minimal and the maximal one are kind of important. And then if you go to, for instance, to quantum information theory, if you go to pure states, so pure states are elements, are norm one elements in a Hilbert space. So if you take several of these, then it turns out that the injective one, the injective tensor norm, which is the smallest one, will be related to a measure of entanglement for these multipartite quantum states called the geometric measure of entanglement. Exactly the same. They are not related, they are the same thing, up to a log. So hence, again, studying this injective norm is kind of important for entanglement in the multipartite setting. So now people are trying to understand this in several directions. So for instance, you can ask, what is the most entangled state on 7 qubits, pure state? Or you can say, well, I take a random quantum state on 7 qubits. What is its geometric measure of entanglement, or equivalently, the value of this injective norm? So these are the questions which are now very, so there are many people doing research around these questions. So this is for pure states. Now, if you go to mixed quantum states, to density matrices, again, in the multipartite setting, it's not this injective norm, the minimal one, it's the maximal one which would be relevant for entanglement, or the projective norm. So already just stating the problem in this way, so thinking about entanglement of mixed states in terms of this projective norm, this gives you already, for free, two of the most famous entanglement criteria for mixed quantum states, the IPhT, the positive partial transpose criterion, and the realignment criterion. So I will discuss these and tell you what these are and how so people have found them by, they said, look, if we do this, then we get an entanglement criterion. But now if you just write the problem in terms of these tensor norms, it's become like obvious that you should try this. So they come very naturally once you write the problem of entanglement in this framework of tensor norms. And once you do this, then you can come up with new entanglement criteria and basically do more around this entanglement of mixed quantum states from this point of view of tensor norms. So these are kind of the topics that like the main results I will discuss and I will tell you about. So you see, it's a mixture of kind of these tensor norms and quantum information theory, and especially entanglement. So there is one topic that it's not on that list and that should be on every talk about tensor norms and quantum information theory, and that's Bell inequalities. So it turns out that one can talk about Bell inequality violations in terms of tensor norms. This is something that also already Cedric did, but kind of it goes into a different direction than it was too much for these 3 lectures, so I decided not to. But tensor norms are very useful also in this non-locality and Bell inequalities setting with like important results like Grothendieck's inequality, which plays a fundamental role in these topics, but that's something that I will not discuss. Good. yeah, so these are some of the keywords which will appear. So today I discussed like norm spaces, a very basic theory of norm spaces in finite dimensions, some convex geometry, and then some examples. So I will try to give as many examples as possible. So basically the main examples today will be the LP spaces, and the equivalent notion for matrices is Schatten classes. The duality is very important in all this theory. So always when you have some space or some norm, you should always consider the dual norm and the interplay between them. This is very important. And tomorrow we'll discuss tensors. Maybe 2 words about tensor rank, although this is kind of not essential for these lectures, but it's kind of fundamental. Then I will tell you about this graphical notation for tensors, how instead of writing coordinates, we use pictures, which is very nice. And then we'll get into the main topic, tensor norms. So the minimal one, the maximal one, the definition of tensor norms, what do we require of them, and then these applications to quantum information theory and to entanglement, in the case of pure states and mixed states. So, okay, good. So let's go into things. So a norm is, so you have a vector, so X is a vector space. A norm on X is just this map which has these properties that you are all familiar with. So one object that we would like to, that we will study a lot is this unit ball of the norm, this B of X. So these are vectors which norm smaller than 1. And actually it's a quite nice feature of these balls that there is a one-to-one correspondence between these norms and the unit balls, meaning that I can recover the norm of a vector just by looking at the geometry of the unit ball, meaning that the norm of X is just the minimum. I have a pointer. Add the pointer. So if you take a vector X in your space, its norm can be seen as how much do I have to dilate my unit ball in order for this dilation T times B of X to contain my vector. So how much do I need to scale my unit ball such that my given vector falls inside? So you can go between these, you can go back and forth between the norm and the unit ball. So these unit balls, of course, are convex. That's the most important property which follows from this triangle inequality. And they also have this extra property that they are centrally symmetric, meaning that if X is inside, minus X is also inside. So 0 is always an element of the unit ball. And actually, any convex set that is centrally symmetric is the unit ball of some norm. So really, we have a one-to-one correspondence between convex sets which are centrally symmetric and norms. So if you don't like norms, if you're more like geometry person, then think of these convex sets which have this central symmetry. Good. So that's the point, that studying these norms is the same thing as a bit of convex geometry. Okay, good. So examples. The first example that you are all familiar with are LP norms. So the vector space is Rn, and the P norm of a vector in Rn is the sum of the pth powers of the coordinates, and you take a power 1 over p. And these are the 3 most important ones. Also, the 4th one is kind of important, but that's something not for today. So the L1 norm, the L1 norm is the sum of the absolute values of the coordinates, the so-called, I think it's called the Manhattan distance. So this is kind of related to probability theory. I mean, we'll see later that it has to do with total variation distance and type of stuff. Then, of course, the Euclidean norm, it's the one which comes from the scalar product on Rn. And the L infinity norm, the max of the coordinates. So you have these 3 norms, and in the complex case, you have basically the same formula, but now the vector space is C to the n. And of course, this has to do with quantum mechanics, because pure states are just unit vectors for this Euclidean norm, for the 2 norm, in a complex space. And now let's take this geometric point of view. Let's look at the balls. So for p equals 1, so these are these 3 cases that I I talked about. So for p equals 1, we have the cross polytope. So this is the unit ball of the L1 norm in 2 dimensions. This is the same picture in 3 dimensions. For p equals 2, we have the Euclidean ball, so the disk and the sphere. And for L equals infinity, we have the hypercube, so a square, a cube, etc. when the dimension grows. So this is the situation for in 2 or 3 dimensions. Okay, good. So now let's go to matrices. So we've seen stuff for vectors. Let's go to matrices, and of course, later I would like to go to tensors. I mean, that's kind of the idea. So for matrices, the matrix version of these LP norms are called the SP norms, the Schatten P norms. So, so basically now the vector space will be kind of some space of matrices, either real matrices, complex matrices. They don't have to be square. They can be rectangular. Either real complex can take self-adjoint complex, and self-adjoint real, like symmetric real matrices. And in these 2 last cases, these are real vector spaces because the field of this vector space is real. So, and how are these norms defined for matrices now? So the Schatten P norm of a matrix capital X, it's, well, the trace of the absolute value of X power P, everything power 1 over P, where the absolute value of a matrix, it's defined as the matrix square root of X star X. So here the star is the mathematician's star. So let me write it down because maybe there's always some confusion about this. So X star for me is what is called X dagger in physics. So X star ij, X bar ji. So it's the complex conjugate of the transpose. And the idea is that this X star X is a positive semi-definite matrix, and you can take its matrix square root and get this absolute value of X. But if you don't like this complex, this matrix square root and all this matrix analysis stuff, you can simply think of that the Schatten P norm of a matrix capital X, it's just the usual LP norm of the singular value vector of X. So what you do to compute the Schatten P norm, you compute the singular values of your matrix X, and then you compute the P norm of the singular value, the usual LP norm of the singular value vector. Okay, so of course, this is kind of a non-commutative LP norm, because if your matrix X is diagonal, then the Schatten P norm of capital X is just the LP norm of the diagonal vector, because the singular values are just the absolute values of your diagonal vector, right? So kind of a non-commutative version of what we have seen before. But just 2 words about the singular value decomposition, which is like my opinion, is the most important result in linear algebra, maybe in some parts of mathematics, I don't know. So it says the following thing. So if you have a matrix, you can always decompose it as a unitary matrix times a diagonal matrix times another unitary matrix. And the elements of this diagonal matrix are positive numbers, and they are called the singular values of X. And what these singular values are, if you like to go back to this geometric perspective, it's that if you take the unit ball of the input space of your matrix, so a matrix is like a linear map between an input space and an output space. If you take the unit ball of the input space, then the image through your linear map of this unit ball, so think about on R2, this is a circle, so the Euclidean unit ball, it will get mapped to a linear image of a circle, which is an ellipse in this case, an ellipsoid in R3, etc. And the singular values are just the size of these axes of this ellipse. So how much does, basically the question is, how much does A distort the unit ball? And the answer is, well, I mean, it can be given by these half axes, and these are the singular values, so sigma 1 and sigma 2. So these are the singular values. Yeah, so this, of course, this is like an opinion. I mean, it's a matter of taste, but you know, like every other matrix decomposition result, like the eigenvalue decomposition, QR, I mean, whatever matrix decomposition result you would have, you can infer it from this. And it appears in all over. I mean, it appears in all these like applied math. For instance, if you have a matrix and you want to have a good rank 3 approximation, this is what you would do. You will list your singular values. You will keep the 3 largest one, throw the rest away. So it gives it's the central object that appears in many results. And unfortunately, this is how it is. We don't have such a notion, such a nice notion for tensors. There is no nice notion of singular values for actually, there are many notions of singular value for tensors, and that's a bad sign because in the case of matrices, they all collapse to this thing. But for tensors, depending on what you do, you have different sets of numbers which characterize your tensors. And this is why tensor theory is much harder than linear algebra. Multilinear algebra is much harder because in this case, we have these singular values which answer most of the questions you can think of about the matrix. Okay, let's look at again at these Schatten norms. So the one norm, it's called the Schatten one norm. It's called the nuclear norm. It appears again. It's very important. We will see today how it appears in quantum information theory. So this is, remember, this is the trace of the absolute value of x as a matrix. So it's a trace of the matrix square root of x star x, or if you want, it's the sum of the singular values. In the 2 norm, in the p equals 2 case, we have the so-called Frobenius norm, the Schatten 2 norm. It's called the Frobenius norm. So you see, it's the trace of this matrix squared. So you get, it's just the trace of x star x. So actually, it's the only one which you can write in coordinates. The sum over the absolute value of the coordinates. So these 2 norms are very easy in general because, you know, the 2 norm of a matrix, it's really, forget that the matrix is a matrix. The matrix is just a bunch of numbers. So the Schatten 2 norm of this matrix is just the usual 2 norm of this vector, of this big vector of numbers, right? So it doesn't matter for the 2 norm if you look at the matrix as a matrix or as if you flatten it to a vector, you get the same number. And the most important of the 3, it's the operator norm. Well, usually we call it just the norm. If someone talks about, well, if a mathematician talks about the norm of a matrix, then usually he or she means the operator norm. So this is the largest singular value of your matrix, S1 of x. And it's also, you can write it as an optimization problem. It's the maximum over all A and B of norm 1, of Euclidean norm 1, of the scalar product between A and xp. Yes? Yes. It is the square root of that expression. There is a typo. So there is a square root missing here and a square root missing here. Thank you. Of course. Good. So these are some examples of norms. I mean, they are the most classical ones. Tell me what other norms you have you like or you encountered in your research, readings, etc. Is there anything else that I left out of this list? Diamond norm, good. So the diamond norm is, well, it's related to the nuclear norm. So the diamond norm is something very important in quantum information theory. It measures the distance between channels somehow in some way. So later today, I will discuss about the nuclear norm for density matrices. So this is we'll see how this nuclear norm measures the distance between 2 quantum states. It's something which makes sense from an operational perspective to measure the distance between 2 quantum states. And the diamond norm is something that measures this between 2 quantum channels, but it can be defined in an operator algebraic way from this nuclear norm, kind of the completely bounded version of this nuclear norm. But yeah, that's a nice one. It has a nice name. So there are, I mean, depending on what you're, if you do graph theory, for instance, there is this cut norm, which is very important. It has to do with computing the maximal cut of graphs. I mean, there are many choices. And basically, I mean, the idea from this that I will try to give you from this lecture is that the idea of tensor norm is that you have these very basic norms on simple spaces, and out of these norms, you construct more complicated norms on tensor products. So the diamond norm is one example. And kind of this framework of tensor norms tells you what are the most relevant examples of tensor norms you can build out of simpler ones. So it's like, you know, going from these atomic objects to more complicated ones which are relevant. Good. Okay. Now duality is something which is very important in tensor norms, but also in quantum information theory. So let's review this quickly. Maybe these are things which are not as familiar, so I can go a little bit slower. You know, if you have a vector space, you have this notion of dual vector space, which is just a set of linear maps from your space to the complex numbers. So basically, if you are a physicist, think of the elements of a vector space as the bras, as the cats, and the elements of the duals are the bras. That's kind of the point. But now, so this is on the level of vector spaces. Now, if you have norms, it turns out that if I have a norm on X, I can construct an associated norm on the dual space, so on the space of these phis, as follows. So the dual norm of a linear form phi is just the supremum over the elements in the unit ball of the original space of phi of X. So this way, I have this very natural norm that I can put on the dual space of my vector space, and this X star and the dual norm, it's called the dual space of my original norm space. So for instance, if you have a scalar product on your space, I'm not assuming this, but sometimes you do. If you have a Hilbert space, for instance, then the scalar product, this induces a nice correspondence and an identification between X and X star. Usually you don't have this. So X star, it's a completely different beast. It's like apples and oranges, X and X star. But if you have a scalar product, the oranges start to look as apples, because to every vector X, you can associate a form, which is just taking the scalar product with this X. So this way, in this situation, when you have a scalar product, think of Hilbert spaces, you have this identification between X and X star, but in general, you don't. And then you see, if you think about this, in these standard cases where we have scalar products, so in Rn, Cn, the usual scalar product, and on Mn, maybe I should have written this. So if these are matrices, the scalar product of X and Y, it's just the trace X star Y. So this is called the Hilbert-Schmidt scalar product. It's like so it's the scalar product you see when you identify this Mn as Cn squared or Rn squared. It's the natural one. And so with this identification, you can identify the dual of an LP space to the LQ space, to the corresponding LQ space, where P and Q are these conjugate coefficients. And it's the same for the Schatten classes. This SP dual is just SQ, where P and Q are 2. Then the corresponding notion for convex sets is also something fundamental in the theory of convexity. And this is called the polar set of your convex set. This is how it's defined. You have a convex set C inside Rn. And the polar of C is just the set of all vectors which have scalar product smaller than 1 with any guy in X. And how it's related to that is that the unit ball of the dual space, it's the polar of the unit ball of the original space. In the case of Rn. Okay. So this duality for norms, it's just polarity for convex sets. Sure. Yes?
Can you explain this a bit?
This thing? Here, this one. So let's look at this. How is it? LP N. This is LQ. So I have the space Rn with the P norm, and I compute the dual norm of this P norm. Okay. So let's take phi. This means that phi goes from Rn to R, and the norm of phi. So this dual norm, it will be just the supremum over all x in LP, so of absolute value of phi of x. Okay? So this is the definition of the dual norm. The dual norm of my phi is just, I'm taking all vectors in my space in LP, and I'm maximizing phi of x. Okay? But in this case, we have this identification. So this phi, this is the same as, so basically phi here is a row vector, right? So phi is in R1. So then this, I can just write it as the scalar product between my row vector and my column vector x. This is this identification between the space and its dual. So now instead of seeing phi as a column vector, I see it as a row vector and I take the scalar product. And the point is that this is just the Q norm of phi. So if I have a vector phi now, and I compute the supremum of the scalar product of phi with all vectors of norm p smaller than 1, the answer is the Q norm of phi. Well, this is the definition of Q, if you want. For P fixed, the dual norm of ln P is again an ln space, and the value of Q is given by this equation. Let me give you a more precise example. So let me take P equals infinity. So let me take phi in ln infinity star. So the norm of phi dual will be the supremum so this is, I can write direct now, it's the scalar product of between phi and x. Okay. So let me write it down because I'm in Rn. So the infinity norm of x, it's the maximal value of the absolute values of x, right? So this is max this is this condition. This is the infinity norm of a vector x, the maximum of its coordinates. And here I have some. Right? This is the optimization problem I have to solve. So let's think about it. My phis are fixed. This is my vector, and I want to maximize the absolute value of the sum, and my x's are just are numbers between -1 and 1. So this is the same as. Okay. So what's the best I can do here? I can multiply each phi I by some number between -1 and 1, and I want to maximize the sum. It makes sense that I should choose either 1 and -1 to make it larger, and which one should it be for phi I? Basically what I don't want cancellations, I want to sum positive numbers. So the best choice is just to take xi to be the sign of phi I. Optimal x. So what I get is just the sum of absolute value of phi, which is the one norm of phi. That's how I went from this P equals infinity to Q equals 1. This is how duality works. Okay, does this help? Okay, so maybe an important point here is that the P equals 2 case, it's fundamental because it's self-dual. If I put P equals 2 here, I get Q equals 2. And, okay, so this is what I just shown. I showed that the dual of the cube is the cross polytope. So the dual of the infinity norm is the 1 norm. So this duality, this polarity for sets or duality for norms has many interesting properties if you are interested in this convex geometry side of things. For instance, it maps extremal points to facets. Let me show you, but it's better if I show you a picture then. So here, I told you that this one, the first and the last are dual to each other. And what I mean by that is morally that this cross polytope here, the ball of the unit ball of the L1 norm, it has 4 extremal points, right? It has these corners. Actually, these corners are in one-to-one correspondence with the facets of the square, right? I mean, this guy corresponds to this one, this guy corresponds to this one, this, and etc. R equals 2 is a bit tricky because there are 4 of them, there are 4 of each. But let's look at the at R3 at n equals 3. So let's look at the cube because we are familiar with cubes because we use dice. So a cube has 8 corners, 8 extremal points. It's 2 to the 3. And it has 6, of course, there are 6 possibilities. When you throw that, you get 6 outcomes. So it has 6 facets. And it's the opposite for the cross polytope. So the cross polytope has 6 extremal points. You see this top one, the bottom one, and there is this base which has 4. And it has 8 facets. Like there are 4 on the top of this top pyramid, and you have the reflected pyramid on the bottom. So this is important. I mean, this is kind of a nice observation, geometrical observation, but when you go to larger dimensions, this is important because basically, so for in dimension n, the cube has 2 to the n extremal points, all the possible sign vectors, and 2n facets, which correspond to these inequalities, which correspond to, well, to n times this. So you get an inequality for each coordinate, so and you have 2, so it's 2n inequalities. And it's kind of the opposite, it's kind of the reverse for the cross polytope. This has a lot of implications for in optimization theory, for instance. Like most of the optimization problems on the cube are NP hard because mostly you have an optimization, like say a convex problem, you have to check one by one the extremal points, and you have exponentially many, so you get into trouble. Whereas these problems become trivial they become linear in the case of the cross polytope. So let's say this has the vertices of the cube are very complex, and the facets are very easy. So checking membership in the cube is very easy. You just have to check 2n inequalities. Whereas optimizing over the cross polytope is hard. It's easy, but checking membership is hard. So it's good to have these things in mind. Okay. So good. So let's talk about mixed quantum states now. But are there any questions about this duality of norms part that we discussed? We'll use this quite a lot later. Okay. If not, then let's move on. And these are things which you are familiar with. So mixed quantum states. So basically, one way to introduce mixed quantum states, well, it depends. Like if you are a mathematician, you say, well, I mean, pure quantum states, it's the unit sphere of a space. This is something which is not convex. State spaces should be convex. So that's one way to do it, but it's not the most natural way. Maybe the most natural way is to think about these open quantum systems. So that, you know, then you cannot say that my talk doesn't fit with the theme of the conference. So at least I have these two lines. So the idea of these open quantum systems, you know, you have some state in a Hilbert space, total Hilbert space, which is comprised of two parts. You have the system you want to study. I call this H system, and you have some environment which you don't want to talk because it's either too complex or you don't have it or some adversary has it, so for some different reasons, but you don't want to talk about this H environment. And so if you only are interested in your H system, and for instance, you want to do measure, you want to have expectation of observables on H system, then I lost my pointer. Then the expectation value of your observable A on H system, tensor with identity on the environment, so I'm not measuring any observable on the environment. Given that the state of the total system is psi, well, the way to compute this is to write the scalar product as a trace. So this is something which seems simple and natural, of course, but you know, it has some meaning hidden behind it. So basically, instead of working with this, instead of seeing psi as a unit vector in a Hilbert space, I will see psi as a rank 1 projection in this, as an operator on this H. So not as an element of H, but as an operator on H, actually as a rank 1 orthogonal projection on H. And now you have this trace of A tensor the identity times this psi. And what you get is, it's the same thing as trace of A times rho, where rho is the partial trace of this psi over the environment. So it's the matrix you will get by acting with the identity on the system part and the trace on the environment part on this bipartite matrix psi. So this is the density matrix. And so the density matrix is a matrix which is positive semi-definite and it has trace 1. The fact that it's positive semi-definite comes from the fact that this projector here on psi is positive semi-definite and I'm taking its partial trace. And the fact that it has unit trace comes with the fact that psi had norm 1 inside H. So we'll see this kind of theme appearing later. So now I have my set of density matrices. Density matrices on a Hilbert space of dimension D are just self-adjoint matrices, D by D self-adjoint matrices, which are positive semi-definite. So this notation I will use to denote positive semi-definite. So and unit trace. So this is nice because this is now convex. You see, if I take convex combination, I mean, this is like one way to see this is that you have this cone of positive semi-definite matrices, convex cone, and then I slice this convex cone with this normalization condition trace equals 1, so I get a convex set. Good. So towards about being positive semi-definite. So A is positive semi-definite. There are, you know, many equivalent definitions, but one of them is all its eigenvalues. So it's self-adjoint, so it has real eigenvalues. And if it's positive semi-definite, if and only if or its eigenvalues are positive, or there is this characterization that the scalar product between X and AX is positive, meaning that A sends vectors to vectors which have acute angles with the original vectors. And there is this, maybe even more fundamental, this is the one I like, that basically you can find the square root of your matrix A. Meaning that there is a matrix B Here I take it in MD, but maybe it's interesting to take rectangular Bs also. We'll see this later. Such that A equals B star B. So this last one is very nice because it gives you a certificate for positive semi-definite. So if you ask me if a matrix is positive semi-definite, how can I convince you about this? Well, I can say, look, because it's positive semi-definite, because you can diagonalize it, and I can argue with some inequalities that the eigenvalues are negative, or I can just show you, look, there is this matrix B, and B star B is A, so that's a certificate for A being positive semi-definite. So, good. Okay, so where do norms come into the picture? They come through this very important remark. So this will be crucial in the last lecture. Is that I can express this condition of positive semi-definiteness with the help of the norm in the following way. Have that X is positive semi-definite if and only if the one norm of X is the trace of X. So let's think about what this means. So X is self-adjoint. Okay. So this means that the eigenvalues lambda I of X are real numbers. Okay. Remember that, so X is positive semi-definite if and only if these eigenvalues are non-negative. And remember that the singular value of X, the singular values of X, let's call them S1. So the singular values for self-adjoint matrices, these are just the absolute values of lambda i's. So the one norm of X, the nuclear norm, it's the sum of the singular values. So it's the sum of lambda I. And the trace of X is just the sum of the lambda i's without the absolute values. This is a very trivial computation, but somehow it's important because I can express this positive semi-definiteness in a metric way with tensor norms, with the nuclear norm. Right. So this is how you can say something kind of geometrical about your matrix X in a metric way with the nuclear norm. Okay, so in general, the trace is smaller than the nuclear norm. Actually, the absolute value of the trace is smaller than the nuclear norm, but you have equality if and only if your matrix X is positive semi-definite. Okay? Good. So qubits now. So qubits are nice because 2x2 matrices, 2x2 self-adjoint complex matrices are nice. We have this basis. So this is so 2x2 complex self-adjoint matrices have 4 complex numbers, but if I put the self-adjointness condition, I have just 4 real parameters. So as a real vector space, it has a basis of 4 elements, and this is the most famous one, and this is the correct basis of qubits. So the identity and the Pauli and the 3 Pauli matrices. So this is a basis, so I can decompose any density, any 2x2 matrix as a linear combination of this. And you notice that the Pauli matrices are traceless. So if I want my matrix to have trace 1, the coefficient in front of the identity should be 1/2. And what's happening, there is a small miracle happening in dimension 2. Is that the condition that rho is positive semi-definite is equivalent to the 2 norm of my vector of coordinates to be smaller than 1. Okay? And this is a very complicated way to introduce the Bloch ball. So now for qubits, we have the Bloch ball. We have the computational basis on the z-axis. We have the plus-minus basis on the x-axis. And any pure qubit quantum state is on the Bloch sphere, and density matrices are inside, are in the Bloch ball. The center of the Bloch ball is the identity over 2. It's x equals y equals 0, x equals y equals z equals 0. So we have this very nice representation for qubits, which doesn't hold in larger dimensions. So in larger dimensions, the situation is more complicated. These spaces have, even topologically, they're different. But if I want to state something about, if I want to tell you the story about the Bloch ball in terms of norm spaces, this is how you should do it. It's, of course, it's very cryptic, but I'm trying to get you used to this notation. So basically what I'm saying is that 2x2 matrices equipped with the one norm, because it's this one norm which tells you about the positivity of these matrices. This space is isomorphic to just the Euclidean ball, the Euclidean norm in R3. We have these isomorphisms between the Schatten 1 class self-adjoint matrices and R3 with the Euclidean list. And basically, this picture is the proof of this. Bloch ball. Proof of this. Okay? Of course, it's very abstract and complicated way to tell you this, but that's how you would talk about the Bloch ball using these norms. Good. Now, in the last half an hour, I want to tell you about an application of this to quantum information theory, just to work a bit with these norms. And the application is distinguishing quantum states. Okay. So let me tell you about an operational problem. The problem is as follows. There's this state discrimination scenario, which I will describe now. Maybe, how many of you are familiar with this? Okay. Thanks. So then maybe it makes sense that I take some time to talk about this in detail. So we have the following scenario. So there's Alice and Bob, and Alice will prepare one of two states. So there are these two fixed states, rho 0 and rho 1, two density matrices of size D. And Alice, what she will do, she will flip a coin, and she will send to Bob either rho 0 or rho 1, depending on the outcome of the coin flip. And Bob receives this quantum state, doesn't know what Alice did, and his goal is to respond whether Alice sent rho 0 or Alice sent rho 1. So this is, in general, it's not a trivial problem, at least, because Bob cannot do measurements. In general, if I give you two quantum states, there is no, in general, you cannot distinguish between them unless they have orthogonal supports. But in general, it's hard for Bob to say whether he received rho 0 or rho 1. But this is kind of the setup. So Alice has this biased coin which gives, with probabilities lambda and 1 minus lambda. If she gets the first outcome, she prepares rho 0. If she gets the second outcome, she prepares rho 1 with different probabilities, 1 minus lambda and lambda. She sends this quantum state to Bob. Bob doesn't know what it is. And basically, he has to determine whether he receives rho 0 or rho 1. And the question is, what's Bob's best strategy and how well can he do in this task? That's something quite important. Good. So what Bob can do, so Bob sees a quantum state, he sees a photon arriving towards him, and he has to answer this question. And if you think about it, he can do many things, right? So he can measure the photon, he can do some post-processing on the data, he can do some random coin flips on his own, he can do many things. But in quantum information theories have shown that you can combine all possible reasonable strategies of Bob into a very simple one that we can analyze mathematically later, which is the following one. I mean, at the end of the day, Bob receives a quantum state, and he has to answer 0 or 1. So he has to find some procedure which goes from quantum states to classical states on 0, 1, so either 0 or 1. And quantum mechanics tells you that there is only one way to do this. It's just to do a quantum measurement, maybe a very general one. So if you perform a quantum measurement given by an operator A, so here I'm talking about P of M. So A here is not a projection, it's just some operator between 0 and the identity, and it's complementary, so identity minus A. And he'll respond that he thinks that Alice sent row 0 if the outcome corresponds to identity minus A, and he'll respond that Alice has sent row 1 if the outcome corresponds to the operator A. So this is the most general thing Bob can do. Basically, his strategy will consist of choosing a good operator A. And what does good mean? He wants to maximize the probability that he guesses correctly. So what is the probability that he guesses correctly? So, well, it's a conditional probability depending on what Alice did. So if Alice has sent row 1, this happens with probability lambda, then Bob guesses correctly using the Born rule if the probability that Bob guesses correctly, it's trace of row 1 times the operator A. And in the other case, if Alice has sent row 0, so this is the probability on Alice's side, then again applying the Born rule, Bob guesses correctly if the outcome measurements corresponds to this operator, identity minus A. So it's trace of row 0 now times identity minus A. So this is just the Born rule, corresponding to Bob's strategy A. Okay. So now Bob has to optimize over these strategies. So what's the operator A which maximizes this probability that Bob guesses correctly? So let's solve this optimization problem. This is known as the Hellstrom or Holivo-Hellstrom theorem in quantum information. That is a statement that the best Bob can do, the probability that so using the best strategy, the probability that Bob guesses correctly is 1/2 plus 1/2 of the one norm, this nuclear norm, of the difference between lambda row 1 and 1 minus lambda row 0. So remember, lambdas were Alice's probabilities of coin flips, and these are the two unknown states. So the so the answer is, let's look a bit at it here. So the answer is always 1/2 plus something positive, because Bob can always just don't use the state and guess. So he gets a probability, at least one probability 1/2, so he should do at least as well as 1/2. And there is this bias, this how much better than the trivial guess Bob can do. And the bias is given by the norm of a difference. And the point here, the important point, is that the norm I should use is the one norm. It's Schatten one norm. Good. So let's see how this works. So let's prove that this number here is an upper bound. Bob cannot do better than this. And then from the proof, actually, you will see that you will see what's the best operator A. It will kind of follow from the inequalities we have. Okay, so what we want to optimize, the set of A's we want to optimize, it's the set of operators between 0 and the identity in the positive semi-definite order, such that A and I minus A defines a P of M. So I want to minimize, I want to maximize this quantity. And I will rewrite this quantity as follows. So I have 1 minus lambda, I can take it out from here, and then I factor out the operator A, which is the guy I want to optimize over. Okay. And this is this quantity which depends on the data of my problem, which is lambda and row 0 or 1. So how do we perform this maximization problem? This is a general fact. So I have the following general problem. I want to optimize trace of x times A for A between 0 and the identity. So the idea when you have this type of problems is that you should decompose your operator x. Maybe let me give you a more. I don't know if. Yes. So the idea is as follows: you decompose. So any operator, you can decompose it as a positive part minus a negative part, where x plus is basically you're taking the positive eigenvalue of x, you're putting them in x plus, and the negative values of x, you're putting them into x minus. So any operator can be decomposed as a difference of two positive operators in this way. And these operators have orthogonal supports because, you know, in the eigenvalue decomposition, you split the positive and the negative eigenvalues. So then I rewrite this trace of xa in the following way. So I have trace of x plus times a minus trace of x minus times a. But remember that now everyone is positive. X plus, x minus, and a are positive. So basically, you know, this negative part minus trace of minus x minus a, I want this to be 0 because I want to maximize, so I don't need this negative part. So I will take a to be 0 on the support of x minus. And I want a to be as large as possible on the support of x plus. But I have this conditions modeling identity, so the best thing I can do for a is to take a to be 1 on the support of x plus and 0 on the support of x minus. So in matrix language, this means a should be the optimal. A is the projection on the support of x plus. Okay. So this is the result of the general problem, the supreme of trace of xa, where a is between 0 and 1, between 0 and the identity is trace of x plus. Okay. So now let me apply this to what I had before. So what I had before, now it's 1 minus lambda plus the value of this optimization problem, which is trace of that operator, but just its positive part. Okay. But now remember that, so this operator lambda rho 1 minus lambda rho 0, the plus minus the minus gives you the operator. So plus minus x plus minus x minus gives you x. So I have this relation trace that I want minus the same thing with the negative part. It's the actual trace of the operator, lambda minus 1. And the absolute value of a, maybe I should write this. I haven't written yet. So if x is x plus minus x minus, then absolute value of x is actually x plus x minus. Okay? How do you see this? Think of the eigenvalue decomposition. The eigenvalue decomposition of x. So I can always split it as in a sum of the terms which have positive eigenvalues and the sum with the terms which have negative eigenvalues. Okay, and this will be my x plus, and this will be my x minus. Okay, this is something very useful, this is a very useful trick. So you see the absolute value of x. If I take the sum, so this is if I get the sum of the two terms and not the difference, I get the absolute value of x. Okay, so I have this formula. So this allows me to relate this trace of the positive part of the operator to the one norm, the trace of the absolute value, the nuclear norm of this difference, and to get the result. Okay. Basically, yeah, don't worry too much about this technical proof. Maybe what's important here is this kind of trick of decomposing in positive and negative parts. Okay, good. So let's look in detail at what happens when lambda equals 1/2. So basically when Alice's coin is unbiased. So she chooses randomly whether she sends rho 0 and rho 1. So in this formula, in the formula above, it's 1/2 plus this norm. So basically if if row 0 equals row 1, so if Alice sends the same state, so row 0 equals row 1, Bob will receive this, and he just has to guess whether it was 0 and 1, but he always receives the same state. So he cannot do better than just like flipping a coin. So this indeed we get this probability equals 1/2, if and only if the two states are exactly the same. So it's really, you don't get any benefit from this one norm. And Bob can guess perfectly, so the probability is 1, of guessing correctly is 1, if and only if the states are orthogonal, because then Bob can just do a projective measurement on the supports of row 0 and row 1 and guess exactly which one Alice had sent. So these are the two extremities. So the conclusion of this computation is that the nuclear norm, the one norm, is the norm which gives you the correct distance to measure, the correct distance between quantum states. So meaning that if you have a protocol which you want to see how far apart two quantum states are, then it's most likely that you will need to use the one norm. That's the correct one, and not the two norm or something else. Now, maybe to talk a bit about quantum channels. So this one norm is also important in the theorem of quantum channels because it has the property that it's contractive under quantum channels. What does this mean? If I have a quantum channel, so it's a trace-preserving and completely positive map between two metric spaces. So it models evolutions of quantum states. Then the nuclear norm is contractive under this on the quantum channels, meaning that the one norm of phi of x is always smaller than the one norm of x. So what does this mean when I look at this theorem here? Let me show you the picture again. Yeah, I cannot have both, but so imagine now you have the same protocol. So Alice prepares one of row 0 and row 1, and she sends row 0 and row 1 to Bob. But here in the middle, there is some noise affecting the state during the transmission. So it means that Bob will not receive row 0 or row 1. He will receive phi of row 0 and phi of row 1, where phi is this quantum channel modeling the noise. Then this contractive property of the one norm means that this bias term here will be smaller with phi than without phi. And this makes sense because, this is like this data processing inequality that if you want to distinguish two things, then it's harder to distinguish them if you add some noise to them. So this is what this contractive property of the one norm tells you, that the best Bob can do after having a noise channel here is worse than the best he could have done without the channel. So the mathematical way of expressing this is this contractive property of the one norm under quantum channels. Okay. So let me leave you with two questions. So here we discussed the problem where you want to distinguish two quantum states. What happens if I want to distinguish k quantum states? So Alice prepares row 1, row 2, row 3, up to row k, with probability, let's say 1 over k. Let's think about the unbiased case. She sends this prepared state to Bob, and Bob has to guess what state Alice prepared. Was it number 1, number 2, up to number k? So here we saw in the k equals 2 case that the answer, the best probability that Bob guesses correctly is given by the one norm. What happens if I go to k equals 3? Is there a norm appearing in this probability here? And another question that you might like to think about is the following one. So the same as in the case before, so we just have two states, row 0 and row 1. But now instead of preparing just one copy of row 0 and row 1, Alice prepares n copies of row 0 and row 1. So Alice prepares either row 0 tensor power n or row 1 tensor power n. So n copies of this, n identical copies of the state. She sends either rho 0 to tensor power n or rho 1 tensor power n to Bob. Bob now has this n copies of this unknown state, and he has to guess. Did Alice's coin show 0 or 1? And what happens when n goes to infinity? So you would expect that Bob should do better if he has more copies because he has like more information on this unknown state. It is the case, but how much better can he do? That's kind of these are two very nice questions related to this state distribution. Good. So maybe I should stop. So I have 10 minutes left, but then I think it's not a good idea to start with tensors. Maybe I should start tomorrow because it's a completely different topic. So let me stop here. Thanks a lot. Yes? So maybe it's I made a bad choice of notation. So here A. So here identity minus A, and A is a P of M. So you know it's a positive operator value. So it's a generalization of quantum measurements. A is not an observable. So what does this mean? It means that Bob does a measurement and the probability, so let's call this outcome 0 and let's call this outcome 1. The probability that, so these I minus A and A, so P of M's describe the Born rule. The P of M's give you the probabilities that come out of the Born rule. So the probability of outcome 0 is trace times this operator I minus A, and the probability of outcome 1. Okay, so in general, what is a P of M? Here I showed you a P of M with two outcomes, 0 and 1, but a P of M with k outcomes are just operators which are positive semi-definite and sum up to 1. To the identity, right? Because these are the operators which appear in the Born rule, so they should be positive semi-definite in order to get positive probabilities, and they should sum up to 1 such that the sum of all probabilities should be 1. Yeah, so A is not an observable, although you might think because I use the notation A and identity minus A is P of M. So A is called the quantum effect. So these two things are called the effects of this P of M. So effects are things between 0 and 1. Here? So the point is that these two operators, x plus and x minus, have orthogonal supports. So basically, I can split A into its part on x plus. So I will look at A on the support of x plus and A on the support of x minus. Now these problems become decoupled. So on x minus, I want A to be as small as possible because it has a minus sign, so I will take it 0. And on x plus, I want A to be as large as possible, so I want A to be the identity on that support. So the answer, the optimal for this problem is A is identity on the support of x plus and 0 on the support of x minus.
It's possible for any A or just for P of M.
But A is an arbitrary operator between 0 and 1 here. But I don't see it. So I mean, if I didn't have this condition, then if I didn't have, for instance, A smaller than the identity, I could take A as large as I want here, so I'll get plus infinity. So this condition of A between 0 and the identity, comes from the definition of the POVM, and this helps me, here it gives me the optimal value of A. It bounds the problem. So again, there is like debate whether where you put the dagger, where you put it here or here. The debate. The debate, there shouldn't be a debate because there is one correct solution, and scalar product should be linear in the second guy and antilinear in the first guy. So if I want this to be linear in the second thing, then it shouldn't have a dagger, and antilinear in X means that the dagger should be on X. But in mathematics, people do the opposite for some reason that I don't understand, but this is the correct way.
No other question?
So if I remember correctly, this sum over its AI dagger AI, right? So AI star AI is equal to identity, or maybe I'm misremembering.
Maybe you are confusing with the cross decomposition of channels.
Yes, yes. Is
So
it different?
It's a different thing. So here AI are to begin with positive semi-definite.
Ah, I see. Right. Thanks.
So if you can think of AI as BI star BI.
Okay, if no other question, let's thanks Yon.
Thank you.